established physicist. He's one of the best in this field. He's not going to come out and say, assuming that the light is a particle, we can explain the black body radiation. He cannot do that. If you were to do that, if you come up with some kind of an assumption that goes against the experimental results, that's one of the best ways you can lose your job. And this is 100 years ago. Not too many people did physics. Not too many professorships were available. There were probably about 100 in Europe in general, if not the world itself. There was no way. Those positions were really tough to get. And it was, once you get the position, if you started to publish like that, you will lose your job just like this. If you're lucky, you would be working high school at some point. And even those jobs were really competitive. All right, there's no way he's going to be able to publish the results as is. He knows he discovered something, but what he discovered means that he's about to lose his job, and he doesn't know how to publish it. He doesn't know how to explain it to his peers. So what he does is he waits for a year, and then he says, okay, this is just too much. I have to talk about it. So how do you talk about it? It's straightforward, guys. What do? You present the stuff, and number one, he puts the curves up on the data and the curves and everything else up on the board. And then he just goes over his mathematics, and the sort of math that he was doing is kind of like, if you don't want people to understand what you're doing, you usually present it mathematically. Most of you guys think that, hey, you don't get math, but the physicists do. I got news for you guys. If somebody does a presentation using pure math, no one fucking gets it. All right, so that's the trick that he employs. He comes up with this real mathematical explanation. Math is so thick that no one's able to get the physics of it. At the end, he comes up with this formula. Then when you actually plot the formula, it looks exactly like the black body radiation curve. The data points match the curve itself, and all of a sudden people knew that he discovered something. And the next step is now you have to publish it. The problem with publishing stuff like that, people will go through your mathematics. There's no way you can fake it. It's not like being in front of people. So he spends another year trying to figure out how to actually present this stuff, because he doesn't want to say that the light is quantized. He doesn't want to say that the light has a particle form. But he finally comes up with an explanation. He says, oh, the light is a wave. It's a transverse wave. But the way the atoms absorb and remit light is quantized. All right, you know that the water is a liquid, but you can actually take the liquid and place it into a glass, and you drink it from a glass. Now it's got a size. You were able to quantize it. All right, so that's what he meant. So the way the light is absorbed and remitted by the atom is quantized, not the light itself. So the atom can only take so much light, and it can just process so much light, and you can only remit so much light. And magically something happens. Theory catches on in 1918. He wins the Nobel Prize. Okay, once again, Wikipedia misses the point over here. A lot more than this something happened in between 1901 and 1918. Number one, physicists, all of a sudden they realized that the light, the energy is quantized, and the black body radiation was explained, but they were okay with Max Planck's explanation that maybe the way the atom was interacting with light was quantized. That process was quantized. And then a second mystery, photoelectric effect. Whenever you shine light onto a metal surface, the electrons will come out jumping, which means that the electrons become ions. So Philippe Lenard is the guy who discovers it in 1905. And then for which he wins the Nobel Prize in 1905. And there's something about Philippe Lenard is weird. He's Einstein's physics professor. The year is 1905. He wins the Nobel Prize. Everybody knows that Philippe Lenard, obviously on campus, every single person on campus knows that Philippe Lenard won the Nobel Prize. And Einstein, he's already working on his PhD in 1905. And all of a sudden, Einstein realized that this is a mystery. So the light is coming in, notice, and then the electrons just go off jumping from the surface. So what is the interaction of light with electrons, just so that the electrons become energized and they jump out of the metal? All right, so Einstein ponders about this problem for a while and then publishes his first paper that year. And this is just about the easiest paper that he's publishing, easiest research papers that he's actually working on. All right, so he was already, at that point, he was 10 years into pondering about special relativity. So that's one paper that he's already working on. And all of a sudden, the second thing just comes up. Once again, this is the interaction of light with matter at this point. He goes, oh, I think I know what's going on. He says, I can solve this problem. All right, so Philippe Lenard, 1905, he wins the Nobel Prize. All of a sudden, this problem, the photoelectric effect, comes to Einstein's attention as he was working on the special relativity. He decides that this is something that he was going to focus on for a few days, solve the problem, and then send in the paper. All right, and Einstein, in order to solve this problem, makes the assumption that the Planck is correct. The light is quantized. He takes Planck's theory as is without his interpretation, because Einstein was able to follow Planck's mathematics, and all of a sudden he goes, wait a minute, which means that the energy is quantized, which means that the light comes in particles. Einstein does not even think otherwise. He's thinking, hey, light has a particle form, not a waveform, a particle form. That becomes Einstein's underlying assumption. So high frequency, F represents the frequency. The frequency is what gets chunked up. Frequency is what gets quantized in essence. When we talk about energy being quantized, what happens? The frequency gets quantized. All right, so this is the frequency of red. So the color red is going to carry a certain amount of energy. The amount of energy carried by color red is going to be this. All right, and this is the amount of energy which is going to be carried by the color violet. All right, so these colors, these waves, the light is going to carry energy in essence. All right, so high frequency light is going to carry more energy. The low frequency light is going to carry less energy. That's what it means. All right, so the light is quantized, which means that you've got these light particles. So the particles colored violet will carry a lot more energy than the particles of red, in essence, light particles of red. And the rest is straightforward. This is known as the photoelectric effect formula that Einstein came up with. It's a straightforward formula. On the left, you got the kinetic energy. In the middle, you have the energy carried by the photon, and then here you have some kind of work function. Okay, so how does this work? Guys, the simplest analogy that I will come up with is a jailbreak. All right, so you're in a prison and you're trying to free yourself. All right, so what do you need? This is going to represent your kinetic energy, how fast you can make it get away. All right, larger your kinetic energy is, faster you're going to be able to move once you break out of a jail, once you break out of a prison. Now, for you to be able to break out of a prison, what you need to do is maybe you have to dig a tunnel. All right, so which means that you have to have enough energy to dig a tunnel. HF is going to represent the amount of energy required for you to be able to dig a tunnel. Where do you get your energy from? Well, you get your energy from food. All right, so this is going to represent the amount of food that you will eat. All right, in terms of how much food do you have to eat, you can actually represent in terms of spoonful of food. When you have an H like that, which means that you're quantizing everything into spoon sizes. So how many spoons full of food you have to eat so that you have enough energy to dig a tunnel, all right? W is going to represent the amount of work you have to do in order to actually dig a tunnel. So this is the amount of food that you have to eat, spoons full, and this is the amount of work that you have to do. All right, so if the amount of energy that you are able to intake is larger than the amount of energy that you have to expand in order to dig a tunnel, that becomes your leftover energy. All right, so if you have larger the amount of leftover energy is, the faster you're going to be able to make your getaway. That's what it means. All right, so that's the Einstein's formula of the photoelectric effect. But everything lies on the importance of this statement. This is the amount of energy that the electron needs to absorb quantized energy. Spoons full of energy that you have to eat is the amount of energy that the electron needs to absorb. And this is the amount of work that the electron needs to do in order to free itself from the metal surface. And if there's anything left over, the electron is going to be able to make its getaway. Larger the getaway energy is, faster the electron is moving, the larger the electricity you will generate, the larger the current is. It's straightforward. So the underlying assumption is the electrons are able to absorb quantized light. All right, so the light becomes absorbed as a particle. It gets absorbed and then it energizes the electron. And then when the electron is energized, it does a little bit of work in order to free itself from the metal surface. So that's exactly what that means. All right, so this becomes the photoelectric effect paper, Einstein's second paper that year. He's about to publish. All right, so let's go back and then let's do a quick review. How many spectral lines from the hydrogen atom? We got 4. This is known as the Balmer series. So what does n represent in this formula? N is right here. N is going to represent the number larger than 3. So it could be 3, 4, and 5, and 6. And these numbers will give you different colors. 3 is going to be red, 4 is going to be blue, green, 5 and 6 different shades of violet. Excuse me. What is the black body radiation law? When things are heated, they will glow. And the color of the glow is going to shift from red to blue when the temperature is increased. So what did Planck discover? Planck discovered that the energy is quantized, which means that the energy comes in small chunks. So what is the photoelectric effect? Photoelectric effect is the liberation of electrons from a metal surface by light. So light incident on a metal surface is going to liberate electrons. So when you shine a light onto a metal surface, you will get current, electricity out of it. That's what it means. So the electrons free themselves from the metal surface. They jump out of a metal surface. So what is the theory of the photoelectric effect? The theory of the photoelectric effect is that electrons will become energized by absorbing quantized light and jump out of the metal surface. That's what it means. So the electrons are capable of absorbing quantized light, chunks of light, in becoming energized and jumping out of the metal surfaces. So the electrons are able to liberate themselves from metal surfaces by absorbing energy in the form of quanta. They're able to absorb energy, quantized energy, or chunks of energy. Now we got questions. All right, so the electrons can be energized because they're able to absorb energy, chunks of energy, or quantized energy. And you know that how much energy that they can absorb depends on the frequency of light. All right, so which electrons are going to be moving faster? The ones liberated by blue light or the red light? All right, so which ones are going to be moving faster? Ones liberated by blue light or the red light? All right, you need to focus on this formula. I guess F here is the frequency. Blue is at a higher frequency than red. Given the fact that the blue is at a higher frequency than red, which means that the more energy is going to be transferred by blue light. What that means is if it transfers more energy, the blue light transfers more energy, the electrons liberated by blue light will be moving faster. So the electrons liberated by blue light will be moving faster than the ones liberated by red light. That's what it means. All right. Which electrons move faster? The ones ejected by blue light or the red light? So it's going to be blue light because blue light is a higher frequency. Higher frequency means more energy is being transferred. All right, so the electrons liberated by blue light will be moving faster than the ones actually liberated by red light. What that means is that the blue light is going to give you more electricity. It's going to give you more current. Faster the charges are moving, the larger the amount of electricity is. So what is the intensity of light related to? Intensity is the same as brightness. What is the intensity of light related to? All right, so this is bright light, this is dim light, brighter light, dim light, brighter light, dim light. So what is the intensity of light related to? It's related to the number of photons or light particles that you have. All right, the bigger the number of light particles you have, the bigger the number of photons you have, the brighter the light is. All right, so let's get back to the terminology. All right, quantized energy means that the energy is coming in particles. Quantized light means that the light is a particle. Particles of light are known as quanta, or particles of energy is also known as quanta. And the particles of light and energy is also known as photons. All right. So when we're talking about photons, we're talking about particles of energy, particles of light. They mean the same thing. All right. So in this case, they got more particles of light, larger number of quanta. All right. So larger the number of quanta, brighter the light is. Smaller the number of quanta, dimmer the light is. All right. So what is the intensity of light related to? It's related to the number of light particles that you have. All right, so which electrons move faster? The ones ejected by bright blue light or dim blue light? All right, so which electrons are going to be moving faster? The ones ejected by bright blue light or dim blue light? Yes, the color is related to frequency. So bright blue or dim blue, it makes no difference. All electrons are going to be moving at the same speed. All right. If it's bright blue light, it's going to have more blue light photons. If it's dim blue light, it's going to have less blue light photons. All right, so in this case, if it's bright blue light, it's going to have more blue photons. If it's light blue light, it's going to have less blue light photons. Electrons will all move at the same speed. How fast the electrons move, their kinetic energies will be related to the color of the light. That's what it means. So does the intensity of light, the brightness of light, have any effect on the kinetic energy of the photoelectrons? No. Electrons, how fast they move depends on the color of light, not the intensity of light. So question number 11, what did Einstein's explanation about the photoelectric effect prove, again, nature of light? It proves that the light is composed of particles. Einstein's theory about the photoelectric effect proves that the light is composed of particles. If you don't make that assumption, you cannot explain the photoelectric effect. So the energy can only be transferred by the chunks of light, quantized light, quantum of light. All right, so if photoelectric effect can only be explained by assuming that the light is a particle. So what's the nature of light if that's the case? Is it composed of particles or waves? Every single experiment during the 18th century proved that light is a wave. Wave phenomena cannot explain the photoelectric effect, and wave phenomena cannot explain the black body radiation. Black body radiation and photoelectric effect can only be explained assuming that the light is a particle. So if that's the case, what's the nature of light? Is it composed of waves or is it composed of particles? It depends on the experiment, guys. Depending upon the experiment, the light can behave like waves or it can behave like particles. Hence the reason why it is said that the light has a dual nature, all right? Meaning that the light has a particle nature. So that's what the physicists decided to agree on towards the end of 1918 or 1919. They decided that the only way to explain it is you have to assign dual nature to light. So the light has a dual nature. It's got a particle nature, it's got a wave nature. So depending on the experiment, it's either going to be like a wave or it's going to be like a particle. So what does that mean? It means exactly that. We don't know. It's got a dual nature. It can assume